continuous now signals, okay? Before that, let me go through this briefly one more time. Okay, let's assume we have an analog signal coming from somewhere, from a sensor. Analog sensor. Okay, so what we have is a continuous signal, so let me draw that here. Maybe something like this. So XLT is a continuous signal. There is a map from in general, or can be sometimes can be from 0 to whatever the finite number in general. Okay? So we have an analog signal coming from the sensor first. This can be, say, velocity, acceleration, or pressure or temperature. Okay, like velocity, acceleration, or temperature, or pressure, and so on and so on. And then we go through a sample. Okay, so we are going to take sample. We are going to measure those analog signal. So we have a sample signal. NT. So let me put this to set. NT. Yeah. So we have analog signal first, and then we take sample with every piece of this signal. half of here, that t equals 0. And then at t equals 1 sampling time, 2 sampling time, 3 sampling time, 4 sampling time. For the discrete, this many call this sample signal. Yes. Okay. So then from 0, 1, we're gonna up to say so 10 samples at every sampling time. And then go through a quantizer. Okay, so that would be for the quantizer, we have to divide the output into some combination level. After quantization, this may go up here, and this may go down here, and this goes down here. And this is go down here, and this will go up here. So let me put this next to Q, N, T, S. Okay, and then after that it becomes a digital signal. Okay, let me give you a few minutes. So we start from a continuous signal. Let me say that, continuous. This is continuous. Signal, x of t. And then we take sample at every sampling time, t sub s. Okay? 0, 1 sampling time, 2 sampling time, 3 sampling time, 4 sampling time. At each sampling time, we record the number, the value of the signal. Up to this moment, these numbers are still real numbers with any arbitrary word there. Okay, so that's the also mark. That is infinite. 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 Real numbers. Can be negative, for example, like say 1.231311109, something like this. Okay? Also can be a pi, can be a square root of q, and so and so. So you can store any number you want. But then for a computer, later on we are going to use computer to calculate, to compute whatever the quantity we want. We have to go through the computation. Okay, and since the digital signal or the digital sensor we are going to use has only finite word length, we won't be able to use infinite numbers of word length to store the value. We can use only, say, 2 bits, 4 bits, or 6 bits, or 8 bits, whatever. Okay, a finite number of bits to store the signal. Then we have to compute this is called the compensation level delta. The compensation level delta is given by or defined by the maximum number of, supposedly, okay, let me assume that this is x max. And this is the x min, for example, supposedly. Okay? Then the correlation level is equal to the difference between the maximum value of the signal, x max, and the minimum value of the signal, x min, divided by q to the n. N is the number of bits you use in your electronic devices, having the measurement sensor, digital sensor, and minus 1. Suppose we have 2 bits. If n, for example, if n is simply 2 bits, then the delta is equal to x max minus x min divided by 2 to the 2 minus 1. So that's 1/3 times x max minus x min. Okay? So after the compilation, the number you are going to store in your memory or in the sensor will be those red dots. Depends on your routing algorithm. Can be the compilation algorithm. The compilation algorithm can be rounding off or rounding compilation. Rounding compilation or truncation. Or something else. But these two are the most commonly used for the rough compilation. So So after the compilation, the number stored in your device's original memory becomes the red bar. Okay? So let me show you the example using the slide very quickly. Okay, are you ready? Okay. The first one is taken from the book directly. The upper part, the upper center, this is a signal recorded from somewhere. It's a local signal, voice signal. Let's assume this is a continuous signal, but actually there's a certain small sampling time over there, but suppose it's small enough, you can treat it as continuous signal. Okay? And then you only consider part of it. So now we take only the time from 1.45 seconds to 1.55 seconds. So somewhere around here. They're very small time. And then now you can see that at every sampling time, we have a measurement. Those circles are the measurement taken at every sampling time. Okay? Every TS. The TS can be maybe 0.001 second, 1 to the negative 3, 10 to the negative 3 seconds, maybe. Okay? Depends on your application. But that's the sample signal. But then once you go through the compilation, since we have only finite work length, so let me do it down to you. The signal received or stored in your electronic devices actually is given by those blue circles. This just depends on the compilation. Okay? This one, up here. These are the signal after the context. They are context signal. Let me show you the others. Okay, I think this is much easier to understand. Okay, suppose we have a continuous signal, analog signal. It's a sine wave, sinusoidal wave. And then we take samples at every 0.1 or 0.01 second, I forgot, sorry. Okay? Originally it should be here. If you only take sample, the sample value should be over here. If you look at my mouth, okay, maybe a little point. Okay, look at the mouse, okay? On the sample, the signal should be at this point, this one. Oops. It only goes through the sample. The signal should be this point, this point, this one, and then this one, and then this one, and then this one, this one. But since it also goes through this quantizer, this quantizer. So this memory, the memory or the device can store the value. At this point will be this value after the quantizer. Okay, you see that it's different from this signal, very clear. Okay. So I think everyone has brought your laptop computer, right? Okay, good. So in order to give you a better idea, so I need you to open your laptop. Okay, I need you to run it. This is a figure in a textbook, figure 8.14. We start from a continuous signal, and then take samples, and then go through quantizer. And this is the arrow between the signal, original analog signal and the quantizer signal. Okay? So the code is on the page 501 and 502. So I need you to run the code now. Have an experience on have a feeling on the quantization and sampling. Okay? Okay, so please open your laptop computer, turn on your laptop computer, and try to run this program on page 501 and 502. Okay? And I think you also need a subroutine, subfunction, quantizer this on, here. This on 599, 499. Okay? Run that program now, please. Have a feeling on the quantization, sampling with the quantization. Okay? Please read it down. Where do you read it? But I asked you to carry that with you, right? What happened, everyone? You don't follow my instruction. How many of you does not have a laptop at this moment? Why? I told you that in the very beginning, right? How long do you need to bring your laptop back to the classroom? 5 minutes. Okay, let's see. What time is it now? Okay, maybe let me keep this next hour. Okay? And we take 10 minutes break. 10 minutes break, you are supposed to bring that back. Okay? Everyone, I made it. Okay? No response. I think you all have a laptop, right? No? But I told you that in the beginning of the class, I need you to bring your laptop with you. Because we are going to run some program in the class. So what should I do? I don't know. Okay, in a 10 minutes break, please bring your laptop to the class, okay? That's why you can do that, right? Thanks. Okay, anyway, let's go back to the previous page. Because I need you to run a program so that you have a better feeling on the stuff that we are talking about. Okay, since this course, since this course only consider analog signal, and then up to here. We don't consider quantization effect. It is too much for everyone here, too complicated. So later on we will not focus on quantization. We will assume, later on we will assume the signal will be sampled, and that's it. Okay? Will be sampled, that's it. And there's a very interesting figure I want to show you. You need to learn that. For the sampling, we mean we discretize the signal in time. So we only take samples at every sampling time. In this figure, we take the sample at every 0.05 second. Take sample, take sample, take sample, take sample, take sample. That's the sampling process. But for the quantization, okay, this include both the sampling in time and discretization in the amplitude of the signal. So along the y-axis, that's the magnitude of signal. Right? But due to the word length, finite word length, we have only finite width. We divide the signal into several quantization levels. So the quantization is a discretization in the amplitude. So your memory can only store the numbers on those quantization levels. Okay? In this case, that will be the circle, the red circle. So the red circle are the numerical values stored in your device or your memory or in your sensors. Okay? So that's something you have to keep in mind. So you won't be confused about, well, what is the difference between sampling and the quantization? They are different. Okay? Again, sampling is a discretization along the time, in the time space, okay, in the timeline, in the timeline. But quantization is a discretization along the amplitude of the signal. Okay? That is the basic difference. So don't be confused. Some of you may be confused. Okay? So I want to show you this very early. Okay? Got it? Okay, another figure I want to show you is if you have more bits. Look at this figure here. If you have more bits, your recorded number or value of the signal will be much more accurate in some sense. See that? If I have only 2 bits, these are the values stored in your sensor, or in your device. If you have 3 bits, then we have how many levels? 1, 2, 3, 4, 5, 6, 7 levels, right? So these are the values stored in your devices or memories after encoding. Become better than this. If you have 4 bits, it's even more accurate compared with the analog signal, right? Okay? So more bits represent more accuracy, but also means more money. It takes money. Okay? It takes money to do this. All right, any question? So up to here, up to this moment, I can only show you some conceptual explanation or conceptual figures. We don't go into the mathematics up to this moment, okay? It's much more involved. It's much more involved than I just show you here. And also, as I told you, the quantization has many different methods. It can be rounding off, it can be truncation, okay? There are many different methods to quantize that the signal, to contest the signal. Okay, again, it's not our point here. So let me just show you those figures. That's it. Okay. Okay. So we'll do this example. Okay, this figure in next hour. I need you to run the code. All right, anyway. Okay, so let's continue our lecture. Here. All right, so let's get to the continuous signal. Oh, sorry. This should be whatever the set. This is better, okay? Much more general. Okay, so let's consider the continuous signal one more time. Okay, so let me follow that notation. So it's I can be defined as a set. Okay, so it's a signal, and it's continuous. If you go to the handbook of mathematics, continuous, that's how P is continuous. Okay, if and only if the function value is equal to the limit. P equals P plus, obviously, P plus. This is the definition for continuous definition. The function value of x of t at, say, t plus equals to the limit t approaches t plus of x of t. Okay, but you don't have to worry about this for the moment. Just assume whatever you can understand about continuous signal. It is continuous, means there's no jump. Okay, that's it. I'll be good enough for the moment. Alright, then what can we say? This actually can be extended to complex values. Okay? But usually this can be the complex values. But usually we consider real values only. But that's also possible. Or this is complex values, the set of complex numbers. Okay? Alright, and then a quick example. Where you have x of t is equal to, let me use 1 to the third. Okay, so this is complex function. 2 times e to the j times omega t plus a theta. So where omega is given positive. That's this is negative velocity. Eta can be usually even though it's a complex function, but it is still a continuous thing. Because if we try to expand this complex function using the Euler's formula, any volunteer can do this one. Gentlemen, how are you? Yeah. No, come on, be a soldier, come on. Come on. Bring your note if you don't know how to do it. Bring your note, please. Could you expand this exponential function using the Euler's formula? We have done this last couple of weeks, right? You should be able to do it. Or bring your note with you if you've done it. Bring your note if you want. You need a note to remind yourself. In the Euler's formula, right? You have taken a note, so you should be able to give me the expression using Euler's formula. This is the base thing. In high school, I think you have learned this already. Did you can look at your note if you want. Did you take the note? Don't tell me about that. You can do it. I'll ask your classmate to help. Find a classmate to help. Find your best friend to help. Come on, help your friend, okay? He didn't know or he forgot how to do it. No, you should be with your friend to support your friend. Your friend comes to help you. Onus equation. Yeah, you were supposed to know that, right? We have given you this onus formula. Okay, how about your friend? Thank you. Thank you. Did you take the note? Be honest, tell me, did you take the note? Your note is at home, always at home. Did you take any note here now? Okay, I have to tell you, beginning you say that it's not a good excuse, okay? Okay, you can. Thank you. All right, whatever you want to say, you always can find an excuse if you want to say that. But I have to tell you that take note is very good. Okay? Got it? Take note. Right? Okay, so now you have the onus formula, right? So you can apply the onus formula to expand this exponential function, which is a combination of sinusoidal wave. But one is in the complex world or complex number. One is another. One is complex number. This is real number. This is real number. Okay, and this one is complex number, including the J here. Okay? So yeah, that's it. This is good. So a continuous signal can be either a pure, you see the imaginary part, can be a pure real number, real function, but also can be a complex number as well, which includes both real function and imaginary function. Okay? So this is very easy, right? Got it? Make sure you know that, okay? Again, I need you to take note. All right, please. Take note. Write down the note. Take the note. Don't just sit there, please. It doesn't work that way. Okay, let's move on to the next part. Any questions before we move on to the next part? Right? All right, now later on we are going to manipulate the functions. But before that, let's have some impression on how do we do the manipulation graphically, okay? So let me. Suppose we have two signals, x of t and y of t. You see that? So here we have two signals, and both are continuous up to this point. X of t and y of t are the signals. Now, if we want to add them up, suppose we do x of t, we perform the operation plus sum x of t plus y of t, or x of t minus y of t. I think that's easy. Okay? So let's skip this and move to the time shifting. This is much more interesting. If I have a function x of t, then I delay x of t by, say, tau second. Delay by tau second. What do I mean by that? Look at the figure here. We have x of t, the red line. Suppose that's the x of t. Now if I shift, say, 4 seconds, okay? No, that is 4 seconds. Yeah, 4 seconds, yes. Maybe 1, 2, 3. Then we move the signal to the right 4 seconds. So this becomes x of t minus 4. So this is the delayed signal of the previous 4 seconds delay. Move to the right. Now, alternatively, if I need to perform the time advance, okay, 2 seconds. 2 seconds, x plus 2. then we move the signal, or move this function to the left 2 seconds. So from -1 to -3. So this becomes the signal x of t plus 2. So this is time advanced. That is time delay. This is time advanced. Okay? So give you the impression how is that supposed to work or to mean. Another one, if I need to reflect the signal, okay, x of -t, what is that? We flip the signal. So again, we start from this original signal. Suppose this is an example. Now if I change the sign of the time, means we flip the signal around the y-axis. Okay, so this is time equals 3 seconds. Now becomes time equals -3. Then 1 second here, now move to here. Okay? So we flip the signal around the y-axis. So this is the flipping of the time. We reverse the time. Okay, alright, let me stop here because some of you want to go back to bring his or her laptop.